Okay, more swag boxes and other things at Reg. Tracy, you can follow her at Hacker Pinup, is based in New York and is a security research engineer at Trenchant, formerly Azimuth, and she's going to talk to you about cell phone networks. So I'll get out of the way because we've already taken a little bit of our time and let her get started.
Well, this is fun. So give me 1 second here and see what's up with this. Naturally. Sorry, yeah, it was all queued up. You know, this is how live theater, live performance in general is just gonna go. So, yeah, right? It says it right there. I knew something was gonna happen. Let me pull this over here. Yeah, but I need to see my speaker notes and they're not showing up over here. Well, and I don't have an external mouse, so I'm just trying to do this with the, I could use some assistance, no? Well, yeah, they unfortunately were. No, wrong way? Is that what? Well, so the good news is we can just skip who I am, I guess, and jump into the networks. All right, I'm just gonna take matters into my own hands. So, because there's a lot to cover here. Okay. And I promise I'm not gonna just try and smush everything together. So, did that work? Absolutely not. Cool. Let's see. Awesome. Okay. Well, it's only 5 minutes. Sorry about that. I like the way she's thinking. Okay. Let's move this one over. Here again. Awesome. That's much better. So I'm Tracy, and now we're friends, so that's cool. And as you could probably see in my speaker notes, I was saying that I'm a little nervous because this is my first talk at ShmooCon. Woo! So I'm trying to think of it as just another opening, another show. So quickly, who am I? Despite what this says, I'm not Jean Valjean. I know they already did an intro for me. I work at Trenchant, formerly Azimuth. I've got about 9 years of experience in telco, and I've split my time mostly doing reversing and embedded dev. I had to submit for ShmooCon this year because of the theme, because my first degree is actually in theater performance with a vocal performance minor. So I was doing musical theater professionally for many, many years, and now I mostly do computer engineering. But theme was too perfect, I couldn't resist. So why should you care about cellular networks, right? I think it's pretty obvious. There's a lot of reasons, but really, mostly, you can't avoid cellular devices. We have them in our cars, we have them on our wrists, and our pockets. Everywhere we go, we have to rely on cellular networks. So understanding them is gonna be pretty cool. I also need to say, disclaimer, is that everything here is public information. I'm not gonna say anything groundbreaking or anything proprietary, but one reason I wanted to give this talk is because like so many times, even in cellular network diagrams, there's just like a blob that's like core network. And not everyone knows what's in that. So in this talk, I'm actually gonna talk about things that are in the whole network, the whole architecture, as well as some known attack vectors. And again, all of the attacks are publicly known, nothing secret here, but now you might know what you're actually looking for if you wanna learn more. So what to cover? So this quote from Spelling Bee was too apt, had to use it. So we're gonna lay out telegraph to telephone very quickly. Very quickly. 0G and 1G, analog cell phones, mobile telephony, circuit switched. I'm gonna cover all those terms. We're gonna go through 2G in terms of GSM, GPRS, 3G in the form of UMTS, LTE, 4G, and 5G. And all of those generations from 2G forward, I'm going to cover some public attack vectors. So here is my favorite image. It's great, and I unabashedly stole it from the Cellular Network's Wikipedia page. And you'll see here our path forward and what we're going to talk about. So we're going to start with NMTS, AMPS, and move forward. And you see how it's mostly on that line at the bottom. At the bottom below that, we have about a timeline, so you can see when these generations were actually happening. And you'll notice at the top, it says like 1G, 2G, 3G, and those are generations of cellular evolution, right? So you'll see that it's 1G, and then below that, you have all these other acronyms. And those other acronyms are also specifications. So we have our generation specification, and then our implementation of a different specification for that generation. So let's cover some background first. Have you heard of the all-American prophet Bell? So I'm going to zoom through a lot of this, but first of all, we're going to start in 1830 when the telegraph was invented. And the telegraph was like a huge deal because it could cover long distances and it proved that we could send a signal over wire over long distances. Super great, but there was only one message per line. And so there were a bunch of inventors racing to get improvements on this telegraph because businesses are involved and they want to get real-time communications, right? So here comes Bell with his background in audiology and musical instruments, and he's like, oh, well, we can just do multiple harmonics, right? That makes sense. So Bell invented this telephone, which is great. So telephone's invented, and then we have to have a network of telephones, right? So before cellular, we had our landline. So POTS is our plain old telephone service. And this is your regular old telephone, right? What most people think of when you hear the word landline. So it's connected over a local loop provided by some telecommunications provider. And POTS, the best thing to think about is that it is a service. So sometimes people use POTS and PSTN interchangeably, which is not quite correct. PSTN is our public switch telephone network, and it's landline network made up of copper telephone lines. Great. So we have our network, which is our PSTN, and the service that's provided on that network, which is POTS. So they're slightly different, but they really are related. And then I put this picture of the marvelous Mrs. Maisel because it's a wonderful show, but also because it's really helpful for me, at least, to really think about the term circuit switched, to imagine these old-time switchboards where people would literally take the cable and connect from one place to the other. So when I say things like an unbroken chain or an unbroken line or circuit switched, it's really helpful to think about these old devices and physically changing that. So 0G, what does that even mean? So 0G is going to be our intro to cellular. We have things like push to talk, mobile telephone service, we have radio common carrier. So 0G, we have no singular standard. It's all over the place. Some systems are two-tone sequential paging, some are DTMF. We have no one thing. So it's obviously not built to actually scale. So then we have 1G. I know we're racing along here. So we have 1G, still analog. And this was a big deal. So we're going to start talking about AMPS, which is Advanced Mobile Phone System. And this was also created by Bell Labs. So in the 1970s, this starts coming around, and AMPS starts using multiple frequencies for the same conversation. So they start really implementing things like channels, which are really helpful in cellular. And then this beautiful thing on the, I guess your left, is going to be the Dyntac 8000X. And this is considered the first cell phone. And it's considered that, 'cause technically there were other inventions, but this is the first time it's actually commercially available. So this is the first time just a random person can buy, oh boy, can buy a cell phone. And this relied on the AMPS network, which is why I put it under the AMPS section. And these are old technologies, but they're still used until fairly recently. So AMPS was happening in North America, and at the same time, in the Nordic countries, we had the Nordic Mobile Telephony. And this was similar to AMPS, but it wasn't very popular. And some of you who are less familiar with telecommunications maybe need a refresher of what big vendors might be out in the Nordic spaces, and that's most notably our Ericsson and Nokia. So they're laying some really great groundwork for actual more cellular, what we think of today. So the cool thing and cool from an attacker perspective about the Nordic mobile telephony system. They had no encryption whatsoever. So you could just stand out there with a scanner and listen to people's phone calls. Eventually they started selling scanners with that frequency band blocked, but yeah, that's pretty fun. So 2G. 2G is gonna, here we are in our timeline. We're just starting to be in the 90s. We've already covered NMT and AMPS, so we're chugging right along. So 2G in the form of GSM. And I know that I just said old tech matters. I even just referenced that in 1G, but a lot of things can fall back to 2G or 3G still to this day. So 2G still matters. This is where we get texting and calls, and we finally have like some standards. We have these actual global organizations that are getting together to discuss what's going to actually last and what's a reasonable standard. So let's talk about the network architecture. So we have our mobile equipment or our mobile station. And this is the device with the cellular functionality for 2G. This is what you think of that you're holding in your hand, right? You are the mobile station with this phone. Then we have our radio access network. And this is what most people think about when you think about like antennas and baseband units and radios, right? Our radio access network in 2G is the same as our base station subsystem. And the base station subsystem contains one or more base transceiver stations and then a base station controller. So you have your mobile endpoint, your mobile station, which then reaches out to this base transceiver station that does some, that's what you think of as the antenna and has usually like a little shed next to it to do some of the processing. And then that hands it off to a base station controller. Base station controller controls a bunch of different base stations. So let's look at what this looks like visually. We have our mobile endpoint, and then that reaches out to a base transceiver station, which then reaches out to a base station controller. Sorry about that color. And that's all part of our base station subsystem. So that's the front part of our network, right? So that's the part before the core network. So I wanted to show you what these looked like so you had some sort of grounding. That's going to be a 2G cell phone, a base transceiver station, and a base station controller. These things are very large. So moving from that front part of our network diagram into our core network, we're going to have a couple more devices to talk about. We have our mobile switching center, which handles our call switching and most of our mobility management, handover, registration, authentication. And it does that. You see how it has those 4 blobs above it? What you really need to remember from this is those are all registers, which are really just big databases that contain specific information. So those are our home location register, which is a large database of information for local users. So that's going to have our activity, status, location, et cetera, for non-roaming users. Then we have our visitor location register, and this is like we had home, now we have visitor, right? These are going to be our roamers. We also have authentication center, where authentication in 2G is not so much a thing, but we do still have verification of our SIM cards, so this is where you keep your puke and your PIN and all that fun stuff. And then we have our equipment identity register, which is a large database of valid equipment on the network. So only valid IMSIs and MSI-SDNs can actually connect to the network because we have this register to check those devices. So again, I'm using the actual terms for these, but really they're just large databases of what should be connecting to this, and so we know our home and visiting people. So when a device goes from one MSC's territory to another, the VLR, the visitor location register, and the home location register are going to do a lot of communicating, right? Most of the concepts of cellular rely on the fact that you're going to be moving around. So those 2 devices still need to communicate a lot and reach out to the remainder of the network so that everyone can keep track of who is where. And then the MSC is going to hand off a bunch of information to our global mobile switching center, which is our last hop before it gets to the public network. So let's take a look at what that is. We're going to go through step by step one more time. So a user would speak into your 2G capable device. That's our mobile station. Then that gets sent to our base transceiver station and our base station controller, which are part of our base station subsystem. That's then going to go into our core network, which contains our mobile switching center and our global mobile switching center. And remember that our mobile switching center has all of those registers. And this is a mobile switching center. So the scale of these things is pretty large. So that's 2G. So let's talk about some GSM attack vectors. So there's no mutual authentication. So GSM requires the handset to authenticate with the network, but not vice versa. So this is how IMSI catchers can come about. So what happens is, so you essentially an IMSI catcher is you stand an attacker standing up a rogue base transceiver station. So when an IMSI is broadcast, it happens from the mobile station, and an IMSI contains a bunch of information, including your mobile network operator, so your carrier, your Sprint, your whatever, your mobile country code, and a bunch of other identifiers. So from this a type of attack where you have, so a mobile station is broadcasting this IMSI out, right, all the time. So it needs to connect to the closest/strongest signal for a base transceiver station. So if an attacker poses as the strongest signal, as the closest base transceiver station, they'll start getting that IMSI broadcast to them, right? So because there's no mutual authentication in this network, what happens is an attacker comes in as a rogue base transceiver station and gets that information from the IMSI. Now, an attacker can choose to just drop that, like in black hole it, and not send it on to the network, or they can choose to try and authenticate with the network by using like a location update request. So the actual base transceiver station requests some information from the mobile endpoint, from the mobile station, and all a rogue base transceiver station has to do is ask the mobile endpoint for that same information and then pass it right back on to the legitimate base transceiver station. And voila, you have a beautiful person in the middle attack. Lovely. So you can intercept outgoing calls, SMS, and the fun thing is that the base transceiver station is actually what determines the encryption scheme. So an attacker can just be like, oh, JK set it to A50, we're not going to encrypt anything. There are also known weaknesses in A51 and A52, which are other GSM encryption mechanisms. And there are some other fun things to do. So GSM is notoriously weak, so we're just going to move right on to GPRS, because it's probably my favorite. So here we are in our timeline, speeding right along. And this is happening in America at the end of the millennium, and you'll see that GPRS is like this weird cutout in this diagram, and that's because it really is 2.5G. And we're going to talk about what that means. It's general packet switched radio. So until this, all of the technologies we've seen have been circuit switched, and that means, remember, like unbroken chain, and it's older technology, right? Now in GPRS, what we're going to see is GSM and then an IP implementation slapped on top of that. So we have these two types of technologies working together at the same time in the same network. This is also where we get push-to-talk over cellular and MMS. So let's talk about the GPRS network architecture. And I left this image at the bottom here because you might notice it's exactly the same as what we had for GSM. Nothing new there. We still have our MS, our base transceiver station, our base station controller, our mobile switching center, and our global mobile switching center. So that part is going to stay the same. Sometimes now our mobile station is going to be referred to as our user endpoint, and that's just a terminology thing. It's all the same stuff. Our BSS is going to remain the same with our BTS and our BSC. And we're going to have our MSC, which contains most of the functionality as before. So now we're going to look at the newer parts, the shiny packet switched features. And you can think of the packet switched part as the internet-y portion. And the internet is really, really great. So for the whole front end, right, we stayed the same. But now we're going to need support for GPRS. And those are going to come in the form of GPRS support nodes. Now, this is going to be our serving GPRS support node, which is referred to as our SGSN. And this is going to do our location and security and access controls, a bunch of our mobility management. And it's going to handle authentication and GTP packets, which I'll go into a little bit more in depth, which are our GPRS tunneling protocol packets. It communicates with other SGSNs, other serving GPRS support nodes, and other mobility management entities. Oh, look, I have it there. And then we have our GGSN, which is our GPRS Gateway Support Node, or our Gateway GPRS Support Node. I've seen it written in real documentation either way. It's another support node, right? It's our last hop before the PDN, before our public data network. And when I say gateway, usually that's what we mean. It's usually the last step either into a certain network or out of the certain network, and usually referring to the core network. So it assigns IP addresses for devices internal to the core network, and it is really thought of as a gateway, a router, and a firewall all in one. Usually, it's very often just referred to as a router. Oh, look. There are also other types of gateways, often depending on the actual operator's implementation, but we're going to zoom through that and just take a look at our network. So again, you see that this whole top part looks pretty similar, except for those registers that we talked about are no longer just above the MSC. We now need our SGSN, our serving GPRS gateway, our serving GPRS support node is going to need to access our home location register and our visitor location register and our authentication. So what we're doing is taking this from just our circuit switch portion and sharing it between the circuit switched and our packet switched portion. MS, BTS, BSC, all the same, right? So now we have that top part is considered our circuit switched portion, just like it was before, and below is our packet switched portion. And then you see how that SGSN communicates to the GGSN, which then reaches out to the public network. So let's talk about some GPRS attack vectors. So you have that same rogue BTS flaw, and I am going to mention this company called P1 Security, and I have a soft spot for them because I took a training with them early in my career. But they do some really awesome research, and I'm going to reference them a couple times in here. So one of the things that they've done research in is GPRS, and they've found some actual implementations in the wild without any encryption. And this was most notably in Italy and Denmark. And this just means that, yeah, again, you can just do whatever you want in that network. It's lovely. So let's talk about this denial of service on this Nokia GGSN. So do we remember where the GGSN sits in our network diagram? It's a gateway. It's our GPRS gateway support node. So it's that last hop before the wild internet. So what happened was someone on the wild internet decided to send in a packet to our core network that had, I think it was, where'd it go? Yeah, non-standard IP options. It's not even like wonderfully crafted. It's just non-standard. And it took down the whole GGSN. Yep, lovely. So this whole cellular area just has no service for a bit. There are also GTP known weaknesses. So the GPRS tunneling protocol has no encryption on user plane or control plane. So GTP has, there are specific protocols for the user plane, control plane, and charging plane. And GTP is what actually sends the commands for creating and attaching PDP context, if you know what that means. But both the signaling plane and the user plane packets are sent in the clear. So a compromised GPRS support node will allow an attacker to monitor and manipulate GTP traffic. So this has led to some documented infrastructure attacks over billing, which is not very well known to the mobile endpoint, to the user. They don't usually notice that for a long time. And protocol anomaly attacks. So on to 3G. Woo-wee. So we have more internet functionality now. We have things like video chat, mobile broadband, and here is where we are in our timeline. So we've covered NMT, we've covered AMPS, we've covered GSM, GPRS, and now we're on to UMTS. So the network architecture, we're going to keep most of GPRS still. You'll notice along the lines, there are only a couple things that get modified in every generation, so we're just keep adding on. So now, our radio access network still does the same functionality in the network, but they have to slap a pretty name on it, so it's the UMTS Terrestrial Radio Access Network now. There's a lot of little subtle changes to names. Our mobile station now is usually referred to as our user endpoint or user equipment, but the MSC is going to stay the same, just as it was for our circuit switched operations. we're going to have our node B now. So instead of our base transceiver station, it's going to be referred to as a node B. And this term node B is going to keep with us throughout the future generations. And we also get our RNC, our radio network controller. And our radio network controller is in charge of a bunch of node Bs. It handles our radio management, a lot of mobility management, adds encryption to user data, and it reminds me of the BSC, but better. All right, so let's take a look at this actual architecture. So here's the network diagram. Looks a lot like our GPRS, right? We still have our mobile station or our user endpoint. And now instead of our base transceiver station, you see that we have our node B, which then reaches out to our radio network controller, right? The core network is going to stay the same. We still have our mobile switching center and our global mobile switching center and our serving GPRS support node and our GPRS gateway support node. So the packet switched and circuit switched portions of our network in our core network are going to stay the same. Really just that radio access portion changes. So let's talk about these attack vectors. So rogue BTS is starting to fall out of style. It's not very targeted. It's kind of annoying. But there are some cool attack vectors in terms of radio resource control now. So radio resource control messages handle the control plane, L3, between the user endpoint and the core network, right? Remember what our radio access and our core network look like. So most messages are integrity protected, but most notably, the ones that are not are going to be our RRC, our radio resource control connection request, setup, and reject and release. So modifying these messages can result in a connection status change for the user without them actually knowing. There are also some remote IMSI attacks where, integrity keys used between the user endpoint and the radio network controller. Those are actually generated in the core network portion of our diagram. So those are transmitted to the radio network controller unencrypted. They're also often transmitted between radio network controllers unencrypted. So that's fun. The integrity of user data is actually not defined. It's not part of our standard. There are a lot of things that are just slightly off in our 3G, right? We have a short time during signaling where signaling is entirely unprotected and can be tampered with. And there is also something called HLR overloading. If you remember what our HLR is, it's our home location register. It keeps all of that information about the home mobile endpoints, right? So the mobile endpoint has to communicate with the HLR, but remember, in order to do that now, we have to reach through our SGSN, our serving GPRS support node. So in order to do that, we have to go through that whole network. Now what can happen is an attacker can send that through, obtain a list, so an attacker can essentially send that through and just resend that message over and over to overload our HLR, and then in that way it'll affect the SGSN and take that down as well. So that's cool. There's a variant of this attack. There's a variant of this attack where, remember when I said that your IMSI contains your mobile operator and all of that information? So what an attacker can do is say, okay, in this area, I can see all of these IMSIs that are specific to Verizon or whatever your provider is, and send a list of those IMSIs with this synchronization request to the network. And the network will be like, well, yeah, these are valid users, and it'll start doing a lot of computation for some of the crypto keys and communicating between HLRs and VLRs and take it down that way. And the thing is that they're known values, so the network is going to obviously prioritize them. The other thing is that then that prevents any other legitimate users from actually connecting to that device. So LTE. So the focus now is super IP based. Like before we were working with circuit switched and packet switched, and then we are now like fully packet switched. And for LTE, it's not really 4G, but this comes up in the late aughts and it's time for long-term evolution. So the reason I say it's not really 4G is kind of fun. And that's because initially this global standard for REL 8 and REL 9 of 4G, LTE didn't apply to, right? Like this didn't actually fit the specifications. But then eventually, later on, this international community was like, okay, fine, it can be called 4G. So that's what 4G LTE really is. It's not really initially what 4G was supposed to be, which is why I don't have it in the 4G section. So this is our evolved packet core, and we get voice over LTE. So the term evolution is going to keep coming up in LTE terminology, but let's take a look at what the actual network looks like. So we have still our mobile station or user endpoint. We have our E node B now. Gotta love slapping that E in front of things. Same device though. Okay, maybe there's slight frequency differences, but pretty much does the same thing. We have our mobility management entity, and this replaces our RNC. And this directs things to the appropriate SGW. It does bearer activation and deactivation, paging, authentication of user endpoints, and it directs things around appropriately. We then have our HSS. Now remember all of those registers? Well, we're going to combine the home location register and the authentication one into our home subscriber server. Makes sense. We also have our signal gateway, and this routes and forwards packets. It looks a lot like our SGSN, doesn't it? It's in the exact same place. And then we have our PDN gateway, or PGW. And remember, our PDN is our public data network, and this device looks a lot like our GGSN did. It's for exiting, for outgoing and entry into the cellular network. It does policy enforcement, LI, packet filtering, charging support, etc. And we have this mechanism for charging support in our policy and charging rules function, our PCRF, but really that communicates with the PGW. So let's talk about some fun LTE attack vectors. So LTE Inspector, highly recommend you read this paper. It's pretty interesting, the things that are found out about LTE. And let's talk about some of the authentication relay attacks they posted. You can impersonate a victim's cellular device and reach to the core network without possessing any legitimate credentials, and they detail this in the paper. Can obtain information and mount DOS attacks, hijack the device's paging channel, and that can even lead to panic attacks. So your paging channel is going to be what those warnings that show up on your phone, you're like, hurricane warning, or like Amber Alert. You know how your phone just does those automatically? Well, your phone is reaching out to try and get those because they're top priority, right? It's constantly looking in the network for these paging messages, and those are gonna pop up. So a panic attack is when an attacker will have a malicious eNode B that broadcasts out all of these messages, and you have panic in a local area. Very War of the Worlds, right? There are also bidding down attacks, and bidding down attacks are going to be when you can degrade service down to 3G or 2G, and those are going to happen still. Those just happen. You can downgrade the services, and that means that those 2G attack vectors are still going to be prevalent. So moving on to actual 4G, and this is often called real 4G or LTE Advanced or LTE Advanced Pro. And here is where we are in our timeline, getting closer to the 2020s, right? So let's take a look at this architecture. And what this architecture looks pretty much the same, right? So here we get IPv6 expansion, adaptive modulation, time varying channels, voice over LTE is predominant, we have carrier aggregation, and if you work in cellular, in recent cellular, you've probably heard the term IMS, your IP multimedia subsystem. But same general architecture, right? We still have our user endpoint, we still have our eNode B, and then that reaches into the core network consisting of our mobility management entity, our home subscriber server, and our SGW, our serving gateway, and our public data network gateway. So, some LTE advanced 4G attack vectors. So we change our signaling from SS7 to diameter, but I'm not gonna go into that because we could have a whole talk on some signaling stuff. There's also VoIP spit flooding, which spit is spam over internet telephony. It sounds as gross as it is. There are a bunch of different types that you can go with, like SYN flooding and UDP flooding. And this is where it gets exciting for me. I like to read about the actual router vulnerabilities that are found, right? So now we have an easier time for our researchers to be obtaining these types of devices and actually tearing them apart. So there are some really fun ZTE info link and an arbitrary code execution bug found in a whole series of routers by a researcher called Takashi. Parameters are not properly checked, so you can just run arbitrary code on them. Love it. There's an auth bypass in that same series of devices, and you know it's bad because ZTE actually admitted to it and changed it. It's a big deal. There's also TP-Link, pre and post auth, command execution. If you follow these things on the internet, you've probably seen these come up. Netgear firmware encryption errors, and then some more fun topics that P1 Security has released. So there's a mobility management entity vulnerability that they gave a talk on this at Hack the Box and noted that this vendor just had the MME keys just hard-coded. So if you know this vendor's MME keys, you could just use it on any of their networks. Gotta love it. And then they also found that there was an MML interface just exposed on the internet from their PGW. So that means that an attacker on the wild internet could reach into this core network and just run some commands. We also have bidding down attacks now, but the thing is that voice over LTE is such a thing that that could be downgraded as well. Cool. I think we're going through this pretty quickly, so I'm going to give you a second to digest our changes for 5G. So we've gone over a lot, but mostly GSM is our circuit switched, and those devices are going to mostly stay the same until we get to GPRS, where we add our packet switched functionality, right? From that, we're then going to go all packet switched, no more really circuit switched. So we're going to change that structure a little bit. And now on to 5G. Oh, you know what? Before I mentioned IMSI attacks, right? Well, IMSIs don't really happen in 5G. What we have now is SUPI and SUKI. And I don't actually know how these are pronounced, but that's fine. So we have our subscription permanent identifier, which is a 15 decimal string, and then you have a subscription concealed identifier. So by having these two identifiers that are not just beaconed out all the time, they're trying to defeat IMSI catchers. It's not quite so simple as just having an IMSI. So 5G changes a lot of things. It's now, right? In our timeline, 5G is happening right now. So now we realize that it's not just cell phones that are on our cellular networks. We have all different types of devices. So the way that these international standards are thinking of designing this specification has to apply to a bunch of different types of technologies. The other thing that is a huge change for 5G is now we have network function virtualization. So we have a bunch of different functions just running on COTS servers. We also have management and orchestration. And previously, this would happen in some different devices, like our mobility management entities, some of our serving gateways, and things like that. But now it's actually part of the specification. We also have the new concept of network slicing. So this is creating logical networks over the same physical infrastructure. So this is because we can expect a car and a cell phone and medical devices. They all have different needs from the network, and users have different expectations from them. So we can create a quality of service slice for that type of device. It's all about converging technologies. So yeah, smart meters versus voice calls, we're going to expect different things. So we also, you know how we had that BTS that transformed into our node B, which transformed into our E node B? Well, now we just want to call it a G node B. So let's look at this architecture. So this is going to be our biggest change. We still have our access and mobility management function. So this is going to be similar to what we had in our mobility management entity. This does most of our subscriber mobility and registration and security. We have our session management function, which does our PDU management. It chooses a UPF and allocates IPv4 or 6 if it's IP-based, but not everything has to be IP-based now. we have our user plane function, which also would have been part of our MME, our mobility management entity, and it's our anchor point for something now called our NGRAN, because again, we just love slapping terms in front of other things. It's still the radio access network. It's still doing the same functionality as it was before, but now it's for new radio, so it's shiny. We have our unified data management, which does our access authorization, registration, more mobility management, data network profiles, and it communicates with our access and mobility management function and our session management function. And we still have to do charging, so instead of our PCRF, we just now have policy control function. And our policy control function also does dynamic policy decisions. So is there any network condition that will affect this user? So let's look at this network diagram, and I know that this looks very different from before. But we still have our user endpoint, or our mobile station. Still gotta have the device. And that still reaches out to our radio tower that does some processing, which now is our G-Node B. Then reaches out to our user plane function. So I haven't really covered planes, but this is still all in the same level, right? At the end of this row, we have our mobility and quality of service flow and policy enforcement. And those communicate with our access and mobility management function. Again, mobility, registration, security. Reaches to our SMF, which does session management, our policy control function, and our unified data management, which tells our access and mobility management function and our session management, oh, lovely, what's going on? Well, to be fair, that was the last network diagram, so. So the next, yeah, awesome. So the next image that I wanted to show you was, if you remember all of those big devices that we had for 2G, for GSM specifically, here's, I think, this is either Ericsson or Siemens, but this is their 5G kit. It's very different in scale. So let's talk about some 5G attack vectors. Okay. So we have this beautifully detailed attack, which hopefully you can see the diagram. The radio access and the core network don't require authentication, so you can do this location sniffing attack. So what happens is, if an attacker places a tool near a target user endpoint, they can monitor for plain text authorization request messages. And this message, beautiful. This message will contain a rand and an auth, right? So as an attacker, I can then I can form this packet that has, yeah, beautiful, build an authorization request message using those two values. So what's gonna happen is as an attacker, I broadcast this fake message, and we have the MAC for our target user endpoint. All of the other user endpoints are gonna come back and say there's a MAC failure, right? But the actual target user endpoint is going to come back with a sequence failure. So fun fact, from that, you could then, an attacker could then glean whether or not a specific user endpoint is in a specific cell. So if all of the messages come back as a MAC failure, it's not in that cell. If it comes back with that different message, it is. There's an attack request injection. Let's see. Okay, I've got 5. There's some battery draining attacks that are really neat, because these are a lot of IoT devices on this network. We can drain those 5 times faster than expected, so that's fun. And AKA attack, which happens in the ring of keys. Yeah, we can still send malformed packets and trigger crashes in 5G core networks. This is still not something that's solved. And then Deloitte gave a talk at RSA about network slicing vulnerabilities, where you can, because there is more public research on 5G routers, you can take a look, and once you get entry into this network slice, you can navigate up looking for other vulnerable devices. Yeah, that's not so much like a real core network attack, so I don't find it as exciting, but it is pretty cool still. So, to review, we've zoomed through a whole lot, so thank you for sticking with me. We covered 0G and 1G, our analog cellular phones, mobile telephony, circuit switched. Moved on to 2G for digital technology, voice and data, still circuit switched, but now we have our user endpoint, our BSS, our MSC, our GMSC. GPRS moved to both circuit and packet switched. We added our GPRS support nodes. When we moved to 3G in the form of UMTS, which now we don't have our BTS, we have our node B, we have our RNC, and we kept our GGSN and our SGSN. Then we moved to LTE. We have our evolved packet core where we like to change things slightly and slap on an E. And 4G in the terms of VoLTE, IPv6, IMS, all of the devices and architecture stayed the same. And then on to 5G, where we had a bunch of virtualization, network slicing, and now we call it a G node B for some reason. And functionality is generally split into functions instead of these large devices. So that was a lot to cover, but I hope you understand a little bit more about cellular infrastructure and these core networks and some of the fun vulnerabilities you can find out about them. That's my musical theater references and my actual technical references. And if there are any questions, we might have time. Yeah? Okay, I think I have 2 minutes. Yeah. Question. Right, so I actually had CDMA 2000 covered in whatever that is, 3G, I guess, and I took it out. So CDMA, actually, I'll bring up we can have this talk. And then I think you can find me after if I don't have time for you. Sorry. Let's find an image. There we go. All right, so you see where we have CDMA 1. What was that? Oh, repeat the question? Yeah. So the question was about CDMA. Hi, Gaston. The question was about CDMA and where it fits in. And you'll see in this image, we have 2G, where it has CDMA 1, and then CDMA 2000 continuously throughout that 2G, and then it also has CDMA 2000 in our 3G. So I was planning on covering CDMA 2000 in our 3G section, but didn't quite have enough time, unfortunately, and I didn't want to quite inundate everyone with all of the acronyms, so I kept CDMA out. Why didn't it carry forward? I don't know it well enough for that. My experience has mostly been in the technologies that I detailed. I cheated a little, so. Cool. I guess that's all.